Welcome to this first short recorded video that we'll be discussing roots in the root finding lecture notebook, part A lecture notebook of the fourth module in Math 1376 that is on computational applications. It is a good idea to execute this first code cell above right away when you get into this notebook to preload NumPy and the pyplot within matplotlib. We're going to go ahead and jump right into it. You should read through these other contents and look at how the notebook's organized. But I'm going to discuss in this first video just the introduction of concepts. What does root finding mean? Simply, it just means that if we have a function f of x, we're looking for the points, call them x equals c, such that f evaluated at c is equal to 0. And that would be called a root of the function. In other words, the roots of a function are simply the inputs that make the output equal to 0. We'll have some lambda functions for simple examples. We only mentioned these briefly in the Part B lecture notebook of Module 3 in the context of list comprehensions, so you may want to review that briefly for some more context. A lambda function is very useful in the context of this notebook, so we dive into them a bit more here. I believe we also looked at them in the prologue lecture of Module 4 as well, but we haven't explored them very deeply. What is a lambda function? I provided links here so that you can read quite a bit more about these if you're interested, but the key points are that lambda functions are simple types of anonymous functions that you just need for a short period of time in your code. And if that's what you need, then a lambda function is probably right for you. You don't have to go through the process of defining, using that def to define some function name. It's just a generic way for us to create functions. We often do assign them variable names like f for just function, but we'll overwrite that function f usually quite frequently throughout the code. But you don't even need the f necessarily. If you have a class or some other function that takes as an input argument a function, you can usually just pass this lambda arguments expression, whatever that looks like, directly in. You'll see some use cases of that in this notebook in particular. So we'll run the code cells below to see an example of a lambda function in the context of plotting the roots of a polynomial. So we'll create a function f, basically f of x. So this is defining what the arguments are for the lambda function. And then we're cubing x, we're subtracting x, and then subtracting 2. So this is x cubed minus x minus 2. That's the function that we're defining. That's written right here. So I'll go ahead and run that. And now I'm going to run this code cell, and we're going to look at the results, and then I'm going to go through this code cell in a little bit more detail. So when I run this and I look at the figure, I see that I plot something that looks kind of like a cubic. I've plotted some lines that correspond to the standard x and y axes, and I've plotted them as black dotted curves. And then the actual polynomial I've plotted in blue, and you'll notice that I have a title and an annotation that are providing more details about the plot. A lot of what we're going to see in Module 4 is involving how to do narrative storytelling with visual plots and annotate our plots to make the visual storytelling of what's going on more clear for the user. So I'm pointing to the approximate root, which is the point that approximately makes this function equal to 0. It's about negative 2.26 times 10 to the negative 3. So that's pretty small. It's an approximate root of about 1.52. That's where it's at. You can zoom in if you like. This is using that annotate that matplotlib widget, which allows us to interact with. I said annotate, but interact with it. So I can just kind of zoom in really close, and you can see, yeah, it's about 1.52. I'm doing some rounding and plotting, of course. So how did I create all of this in this code with these various plot commands? Step 1 was to plot the curves. So I created a figure, and I have a figure size, and I'm doing a figure number of 0. So you notice it's figure 0 here. That's corresponding to this num argument. I'm creating 100 points uniformly spaced between negative 1 and 2 for x. And then I'm just plotting x and f of x. And I'm plotting it as a blue curve with a line width 2. If this was all I had, if I took the rest of this out, so if I commented it out, that's what the plot would look like. But that plot doesn't have so much information. It doesn't quite tell a story that we want to tell, and the story we want to tell in this notebook is about roots. So let's bring the rest of, let's bring the rest of that back. Let me just go ahead and uncomment out. There we go, that code. So these two lines of code are plotting some axes on our plot. So we're using a vertical line that is positioned at x equals 0. So this is basically when x equals 0, that's the y-axis. So you're positioning the x point for a vertical line. It'll have a line width of 1. It'll be a dotted line and be black. And then I do a horizontal line at y equals 0, which is of course going to be the typical x-axis, and the rest of these arguments are the same. That was what was responsible. So if I rerun this again, for this vertical and horizontal line. And then the approximate root, which is something that I found with a bisection algorithm, and we'll get into that, is defined as the variable c. And then I use a scatter plot to plot the point c and f of c, and the size of the scatter point that I want is made to be 70. It's going to be a red marker, and I'm going to make that marker a square. That's what that S means. This is the color red. You can look up more about this by just Googling matplotlib scatterplot, and you can see these various options for the colors and the marker style. So I can change this, by the way, so 70, if we just look at it, that's that square, and it's red. If I make it, let's say 10, it'll be really small. See, you can hardly see it. If I make it 1,000, then it's kind of ridiculously large. So you play around with these things, and with the plot that I have, I thought 70 looked about right. And there you go. I think 70 was a good size marker for that. So this is just plotting the stuff that is related to the figure, the axes, and the point that's the approximate root. The rest of this is just about the annotation. I created a string variable for the title. So this is the approximate root, and then I'm using how you can put in certain types of formatted float information for the numbers, how I'm formatting various values like f of c and c to make this title here. And then I just plot I use the plt.title command. I'm passing it that title string, and I'm specifying a font size. You can increase that font size. You can play with the title string. You can do a whole bunch of other stuff. Notice that I have to use this R command right here as part of this string, because has to be a more raw string in order to make the approx symbol appear correctly. If I got rid of this R right here, and I plot this, you'll notice nothing is showing up because there's an issue with the rendering of this. And if that's happening, well, why is that happening? Notice what happens if I put that R back. It comes back. So there's an issue with the plot if I don't have that R. So if you're using a fancier symbol from tech, like an approximation symbol, then you need to use this R here so that this is rendered appropriately and the image shows up correctly. Then what I do here is I use a dictionary to define different properties that are going into the annotation of my plot. So I'm creating a bounding box, a dictionary for my bounding box, which is this box that's bounded with a red boundary line and a blue backdrop in white font. So notice it's kind of a rounded boundary. So that's the box style, it's round. The face color is blue. The color of the edge, if you just do color, that's going to be the red. I create an alpha of 0.5 and a line width of 2. And if you say, well, what's going on with this alpha of 0.5? What happens if I make it, let's say, 0.75? Notice that blue got a lot darker. It might be imperceptible at first, but I'll go ahead and zoom in. Oops, I don't think I quite got the right thing. Oh, okay. Well, hopefully you can just see it here. The zooming in wasn't quite working. This is a very blue. It's very dark. And I just liked at 0.5, it made it a little bit lighter. See, it's a little bit lighter there. For me, as a personal style preference, I just thought it looked a little bit better at the 0.5. An alpha parameter when you're doing annotations is usually something controlled to the transparency of the color. And if you make it much smaller, usually do it between 0 and 1. If you make it 1, it's very bold, it's very dark. And I don't know, I just feel like it draws your eye too much to this as opposed to what it's pointing to. I thought the 0.5 was a good compromise. If I go to something like 0.1, it's very faded, right? And then it's almost useless. I thought 0.5 was just a good compromise. I thought it blended well with these other colors. I also have some arrow properties that are defined as a dictionary. I have an arrow style that's used. And again, you can look this stuff up in terms of Googling how the annotate works in Matplotlib and look at the documentation and read about it. So there's different arrow styles, but this is what's giving this arrow style. I want it to be black. I also want it to be kind of transparent because I don't want to draw too much attention to it relationship to what I'm trying to point to. And I also have this line width for it. Again, I can make that like 1. Notice it's a very thin line, but I don't think that looks so good. So this is just stylistic choices I'm making based on what I think looks the best. But feel free to play around with all of these and look up what other values you might like to use. And then when I actually go to use the annotate command, I put in the text that's going to go into this annotation. I describe the font size here at 12, right? I can make it 20. Again, I think that's way too large and it draws its attention too much to this and less to the root that it's pointing to. So I thought, again, 12 was a good compromise. The position of what I'm pointing to, so this is where the arrow will point to, where the text is going to exist. So I'm taking minus 1.25 units from that C value, which is about 1.51. I'm stepping to the left basically by negative 1.25 or 1.25 to the left, and a Y value of 1, right? So that it sits above the axis and then points down to the curve. If I made this negative 1, you'll see that this sits below the axis. And again, I just didn't think that looked so good. So I like to have it above. The color that I'm specifying here is the text color. And then I use the bbox and arrow props keyword arguments within annotate. And I pass in the bbox and arrow props dictionary variables that I've created up here. So that explains all of what's going on in this code. I think the way to learn this is you just have to kind of play with these values, choose different positionings of things, and see what you like best. These are just my own stylistic preferences. I think it does a good job of annotating the plot and saying what I want to say in terms of what the title is, this annotation, this arrow, this scatter plot. It all goes together. In the end, most of the things that we're coding up in this are related to annotations and extra things added to this curve plot. Now, this leads us to this next part of this video, which is a plotting tool, plotting tools, a plotting tool class for roots. So for a lot of different functions F, you may wish to repeat the above plot to tell the story about where the root is and visualize it. But you certainly don't want to write out all of this code again, right? That would be kind of a pain in the butt. So we don't want to do that. The above code also had some hard-coded elements to it that were based on our prior knowledge about where the root of this cubic polynomial is located. In more general cases, we may want a plotting tool associated with a function that allows us to quickly explore where a potential root may be before we even know where it is. We're just trying to guess and to get an idea about where to start one of our algorithms to approximate and find a root. Now, we could just functionalize the above code. However, we are interested in pursuing root finding problems in this notebook where a particular function does not exist in isolation from specific types of data like its roots. When various, let's say, types of things are intended to be used in a more integrated manner so that there's lots of data and method attributes attached to them, this is a good indication that we should at least consider the use of classes to organize these various things as data or method attributes of an object. In this case, we create a class of plotting tools associated with a function that is useful for this lecture notebook. Again, it's not necessary, but it just allows us to get more practice with using classes in object-oriented programming, and that's one of our additional goals in Module 4. So in this code notebook below, in the code below, note how we created a class with fairly short and modularized method attributes that each serve a specific purpose in relationship to the current state of knowledge we have regarding the root. As a suggested activity, add more information to the doc strings and provide more useful code comments wherever they are missing. In so doing, you're really going to go through all the lines of the code very carefully and think about the proper types of documentation that are useful and relevant for what we're doing. I think that's going to help drive home some useful best practices. And the code commenting that was shown in the prologue lecture notebook involving like the polynomial activity and the common functions module that was imported are good starting places for you to see how you should do some of this code documentation. But let's just kind of dive right into it. I don't want to have too, dwell on that or detract from really what the code is here. So we're going to create the class, and again, notice the way we do our naming. Plot tools for roots. This is the standard way you should do naming. Sometimes it's you want to break the rule, but the general rule is for classes, use capital letters on each of the words and put all the words together. So it's capital P, capital T, capital F, capital R, plot tools for roots. That's the class we're creating. We initialize it with just a function. And maybe we have no idea what the root is. So this could be a none type initially. And then we create the data attribute that is the function, which could often be a lambda function. And then you may find the root by some method that we're doing in this lecture notebook, and then you would set the root. And in that case, you would call this method where you would pass it a value, like the C value that is 1.521 approximately here. And then you would set that there. And then you could call also a plot method that is going to create a figure. You can set the figure number, and there's all these various other commands. And you can look at showing the root and annotation. And it will also potentially clear the figure so that you can remove previous annotations if you were going to replot things. Then I plot the typical x-axis. Notice I'm not plotting a typical y-axis because the root may be so far away from x equals 0 that our x-min and x-max may not include 0 between them. In that case, I really just want to make sure to plot the x-axis because that's where the function is going to cross if it's ever equal to 0. I choose to create a number of x values to plot, what I call the xplot array, from xmin to xmax with endpoints, and that endpoints is defaulted to 100. And then I plot those points. I plot the function f, that's now a data attribute, but it is a lambda function or some other function I can evaluate. And I evaluate that at those array of x values. And then I plot it according to whatever color, line style, and line width are passed to this function. But I've defaulted a number of them so you don't have to set them. But if you want to change them, you can. You just have to pass them when you call this method from the object. And then if the root data attribute is not none, if it's not none, because it might be none, and we've decided to show the root, meaning this command is set to true or was left default as true, then we would do our annotation. And in that case, we go to plot, right? This is now we plot with the annotate is true as well. We're passing annotate because maybe we just want to plot the root, but we don't want to annotate. So if this annotate was false, what it's going to do, I'm just going to show you in terms of this plot. If annotate was false, we would plot the root, we'd show this red square, but we wouldn't do any of this annotation with this box and this arrow. If the annotate is true though, we also want to create this box and this arrow. So we go to plot the root, we pass this annotate as an argument, like what was shown here. We use that scatter command to plot the root, the function evaluated at the root, as a marker of, that's a square, that's red, of size 70. We then create our title string and our title, just as before. And if annotate was true, we then add the plot annotate. And there we have our bounding box and arrow props dictionaries. And we decide some information based on the size of the plot, like what are the ranges of y values? What are the ranges of x values? And we use that to figure out where to position the text relative to where the root is. That's what that information is used for, because it's unlikely that in general plots, subtracting like 1.25 and using 1 as the position of this box is a good choice. These were hard-coded in here. So I needed to learn something from the axes themselves. I needed to say from that plot, give me the limit of y values and the limit of x values, and that's going to determine a y min, y max, an x min, and x max. And then I figure out the ranges of these, and I subtract off basically 35% of the range of x values to position this text to the left of the root by 35%, and I position the y value 1/10 of the way up the y range. All right, up above 0, 1/10 using the range, 1/10 of the range there. So that's what we do there. And then we pass everything else as the same. So if we run this, that might seem like a lot. You might have to watch that part and go over this again. But this is where, again, I suggest adding code comments, adding more descriptive doc strings. This is very useful for you to annotate the code with code comments and doc strings to understand all this. But it might take a little bit of going through this a few times to fully understand how we parsed it all out and made these different choices. So here I'm creating an fplot object based on a particular function f. And that particular function f was the one that I created up above. I'll just scroll up. It's still this lambda function. I haven't changed it. And so now when I run this code and I look at this, I can create this matplotlib widget. So I have an interactive plot. From this object, I can just say, hey, plot from -1 to 2, because maybe I have an idea that that's where the root is. And you plot it, and you maybe could look right here and say, oh, you know what? Based on that plot, if I just zoom in and I do some visual inspection, I could look at that and say, oh, you know, it looks to me, look at that, 1.52, 1.522, maybe about 1.521, especially if you have your cursor over here. You might look down at this text right here where my cursor is there. You might go, 1.521 is a good approximation to the root. So based on that visual inspection, I might now set the root to be 1.521. So then when I plot again, because I have show root is true and annotate true, and the root is no longer none, it will actually plot the root and annotate. So if I run this again, I get back to the type of plot that we saw before. Of course, notice the difference is I'm not plotting that y-axis anymore. And now I can also say plot it, but set that annotate to false, and do this with figure 2 again. So there you go. So there's the root plotted, but I don't have the annotation. I do have the title of the plot, but I don't have that annotated box with the arrow. And I can also plot it once the root is set. I could still say I don't even want to plot it. I just want to plot the function. So I say show root false, and then there you go. It goes back to just the original function. Now here's an example that really illustrates why we do not want to plot the typical y-axis. And notice I have this anonymous function, this lambda function. I actually never defined this as a function f or anything. I'm creating an object of this plot tools for roots, an instantiation of this class as fplot_2. And I'm passing it this function that is x minus 2,000 times x minus 5,000 times x minus 10,000. So this is a cubic with 3 roots at 2,000, 5,000, and 10,000. Okay, I want you to pay attention to the y-axis range. It is in units of 10 to the 11th, meaning a 1 followed by 11 or zeros, I think, or is that right? 10 zeros. It's a lot. The largest value of the function here is about -10 billion. In other words, for x between -10 and 10, the function never gets closer than a distance of about 10 billion units from the x-axis. There you go. There's our x-axis plot, and here's the plot of this function. It's pretty far away from 0. And so you go, okay, all the roots of this function exist. You know, it's at 2,000, 5,000, 10,000. So they're pretty far away from x equals 0, which is where you would plot a typical y-axis. If I plot this function between 1,000 and 11,000, I will encapsulate it where all of the roots exist. Now it looks like a typical cubic function, although you can see this range of y values is quite large, 10 to the 10th. So there you go, but I have 3 roots that I can possibly choose from, and we do have knowledge of these roots. I could set one root to be 2,000. By the way, I'm saying try using, here I use 2,000 point as opposed to just 2,000, which would be an int, so this makes it a float. Let's just go ahead and run this first. And look what happens when I set that root and then I say to plot it with the figure number 5, notice figure 5 here, between 1,000 and 3,000. And it will annotate the root there. Now you could change this range. You could plot this like 1,000 to 10,000. But then you're plotting these other roots and you're kind of, where we're sizing things, this is kind of off the plot, this annotation. So it doesn't look as good. It's better to try to like create the plot where the root is somewhere in the middle of these ranges. It just makes the more nice annotated plot. with how we're positioning the annotation. As long as this root is like on the halfway point in the plot or more to the right-hand side, this annotation will generally look good. Otherwise, it's going to look probably a little gnarly if it's kind of too close to the left-hand side of the domain, because we're offsetting this annotation to the left. So it can make the annotation appear like it's off the figure entirely. I'll just go ahead and make this 2000. Let's look at what happens. Well, we got the root, we showed the root, but what's going on? We're getting a value error here. When we go to call the plot, look what's happening. We're saying precision is not allowed in an integer format specifier. What's happening in the annotation is when we create the title, and you can notice the title is not there, is we're saying to format the root object as if it was a float with 3 decimal places of precision, right? Something like that. That's what this is trying to do. Well, when you pass it an integer, that's going to be a problem. But it gets fixed here, and notice it's saying it's in this format where it's like 2 times 10 to the third, but it's only doing that format for a float. Sorry about the scrolling there. So at this point, this has shown you how we can create this object, how we can, based on a function that we could then plot, we could choose different ranges of values. And then from those ranges of values, we can try to figure out which ranges of values seem to produce a function that passes this dotted black curve, which is the x-axis, because that's where a root is. We could zoom in, try to approximate it, set the root, and annotate and say that's where the root is. So that's, in some sense, a description of a bracketing method, which is the first type of root finding method we're going to discuss, where we look for values where on one side of the root, the function's negative, and on the other side, it's a different sign. We've bracketed it, the root's somewhere in between. Then we try to approximate the root. In this case, we were doing it by visual inspection or prior knowledge. And then we can annotate our plot, do some storytelling and saying, here's where the root is and here's its approximate value, and give the user a nice visual piece of information that tells them about what's going on with the root. This, of course, does not answer why we should care about roots. I described that here with some motivating examples. I'm not going to read this to you in the video, but I do recommend you read it because it is very important. They're particularly important in optimization problems because we often find roots of derivatives, which is something that you saw in Module 3 in the Part C lecture notebook, where we found that roots of derivatives correspond to where the functions have maxes and mins. But how do we actually solve these roots? Well, there's plenty of root finding algorithms. You can click here to read about quite a few of them. Most of the algorithms are iterative, meaning that we need to write loops to implement them. But we generally differentiate between what we call as an iterative method and a bracketing method, even though bracketing methods do involve loops. We will talk about bracketing methods first, but that will be the subject of the next recorded video. Thanks for listening to this one.